This meeting is being recorded.
Okay. Yeah, so welcome back from our your all's fall break here. So yeah, we just have the one day this week in class. I think we'll finish up probably the stuff that we'll talk about for Rasp today. We'll do some more, start off with another example that'll help get you going for some of these later problems down here in the assignment. And then we'll talk a little bit more about the why to care about Rasp thing, about like, what do we now know about transformers that we didn't know before? Before doing that, though, there was this the project proposal thing due today, really, but very few of these actually posted here. So please get those posted. There's not going to be points off or anything for not getting it done on time, but this will be the main sort of grade in your class. And so I want to make sure that everybody's on track for this. If you still do have like specific questions about what you want to do, then happy to meet with you after class or in office hours or some special setup time to talk about that. But yeah, this getting this done here should be your top priority for this class. Maybe, and then other administrative thing is that I said I wasn't exactly sure when we'd make the due date for the homework assignment here, but we will make it due this coming Sunday. My sense is that if I make it due any later than that, then people just won't start until next week, and you'll forget everything about the Rasp stuff. So I want it to be due this weekend. So this Sunday for the this homework, and basically everybody is late on the project proposal. Any questions on anything administrative?
The project, like other than making a proposal, will it just be kind of like we work around on it until the deadline, or like big points?
Yeah, mostly you work on it on your own. I might do one or two more just like check up things, but I hope to be fairly hands-off on this. My hope about being fairly hands-off is that it gives you all the freedom to do things that are extra interesting and cool. I don't want to like tie people into particular deliverables that just sort of wastes your time from doing the actual cool thing. I realize though that probably that's going to result in people procrastinating too much. But that's a thing that you need to get over, be able to work on these sort of long independent projects. And so, yeah, no, there might be like one or two more small checkup things like this, but no major deliverables for the project until it's due. But also, again, happy to, like, if as you're working on it, you come to a sort of fork in your project where you can decide different ways to go and what's the right thing to do, what would be best. Happy to talk to people one-on-one about those sort of things and what makes sense for your project. Good question. Any other administrative-ish sort of questions? Yeah, Alex.
So
definitely not an hour. It depends on how much time you need. I could see, my guess is that like the average presentation of what you do takes like 15-ish minutes to walk through things. Yeah, so it's definitely during finals week. I haven't decided yet if we'll do it like in class as a group and you present it to everybody, or if you just do it one-on-one with me. And part of my decision about that will be like based on everybody's projects, whether I think it will be beneficial to everybody to see everybody else's presentations, or if it's not that way, then then we'll do it more one-on-one. Good question. Any other questions, administrative stuff in the class? Okay. Then let's do a little bit more. Let's see, I'm scrolling here through the topic 5 Rasp thing to this part about examples from the standard library here. And a lot of the programs that I'm asking you to write in Rasp come from the standard library. So maybe I'll start first by showing you where the standard library is located in Rasp. I'm gonna switch my screens here. We'll do this screen, make it a little bit bigger. And so I'm in the Rasp folder right here. Let's break out of this. And so this is all the files just standard in the Rasp repository. In the Rasp support, ls rasp support, there is a file rasplib.rasp like this. Rasp support / rasplib.rasp. This is their standard library. All of these things, all these functions, all of these SOPs become preloaded in Rasp when you load it up. So you're allowed to use any of these functions to implement anything. And it can also be useful to you to read through some of these functions to see how they work, because a lot of the things that I'm asking are going to be similar, inspired by these functions in some way. So understanding how these work, will help you implement some of the things in your homework assignments. I want to take a look at this average function right here. Where did my cursor go? This average function. We'll walk through how that works. And so I'll repeat it up here for you to take a look at. And then we're going to do a modification of this, which is doing like a running average. And we'll see some techniques for how to deal with the situation where you only want to work with tokens that you've seen so far. So working in a more like auto-generative environment. And that technique, there's I think 3 problems in the homework that you'll have to use this technique for. The original Rasp library doesn't use this technique at all. I think actually we are probably the very first people in the world to consider the Rasp programming language in an auto-generative sort of situation. So there won't be like any other reference material that you'll be able to look at other than what we're going to talk about right now. So we'll start again talking about this average function, what it's doing, and then we'll talking about this new technique for how to deal with the auto-generative situation or things that you've seen so far. And again, the purpose of what we're talking about right now is directly related to your homework. Down here at the bottom, there's 8 problems that I've given to you that you'll have to implement for Sunday. So the average over here, relatively simple. Copy that, and I guess if we come back over here, /rasp.sh to run this. I can't paste it directly in here because if I do that, then we get this error, cannot set reserved name average. This is a reserved name because it is in that standard library. But we can take a look at the code here and still walk through what it's doing by just typing it in on the command line down here. So there's a very simple program right here, just aggregating, and then this full S and the sequence right here, the thing being passed in. Let's first just take a look at what this is actually doing. So the sequence, again, is something that I'm passing into this function. It's going to be an SOP that I'm passing in. Again, in Rasp, there are 2 SOPs that are built in, indices and tokens. And we can do that set example command to change these values. Set example, do hello world now. And now the indices and tokens have been updated. And if I do the average of indices, it will compute the average of all of these things right here, all of these numbers, and store that in just a single, or we get a single value here that is repeated 11 times. 11 times because there are 11 things inside of our SOP, and these functions, again, can never change the size of an SOP. That's one of the properties, weird things about programming in Rasp, is that our SOPs, these sequences, they never change in size. And the reason things are that way in Rasp is because, again, there's this bijection between Rasp programs and transformers never change the size of their output. So average indices gives me something like this. Maybe before I get into like review or go into the implementation here, any questions about anything that I've seen so far, we've talked about so far? Just remind ourselves about what's going on in Rasp. User?
Is there documentation for the standard library functions?
Question is there documentation for the standard library functions? And the answer is this is the documentation, the source code. This is, again, the total number of people in the entire history of the universe who have used Rasp is somewhere between 100 and 1,000. And out of all those people, probably 90-ish% of them have PhDs and do programming language research professionally. And so this is, yeah, what they consider to be good documentation. So the thing to do is to just read it, walk through the lines one by one, see what those lines are doing, and then try to understand why the line is doing what it's doing. Again, too, another thing about Rasp is this is not something, not a tool that anybody would use to actually work with something like the OpenAI models or the Llama models. This is a tool to help us understand what's internally going inside a transformer, what a transformer is like in principle capable of, and not a tool to like make ChatGPT more effective. It's a tool to help us understand what ChatGPT can do. And after we talk about this example here with the averaging, we'll see some more, we'll talk about how this is helping us understand what ChatGPT can do in principle. But good question. So here, the averages, indices. Again, this is the source code right here, just this one single line right here. This sequence comes from whatever's passed in right here. Full S is something that we'll need to remind ourselves what it is. We've seen it before, but full S is a selector. And it is the selector, the reason why it's called full S, it is the full selector. It is the selector where every entry in this matrix contains a 1 inside of it. This matrix right here is, again, commonly called the attention matrix. And we have a 1 here if somehow we're representing true, and a blank value if we're representing false. And the values up here, the hello and hello down here, are the tokens, value of tokens, but they're not the value of the thing that we were using to generate the selector right here. Selectors are created with this select statement. And in this case, the way this one is created is select 1, 1, equals. That with the select statement, you can either pass in an SOP right here, or you can pass in what's called an atom, which, as an example, the number 1 is an atom. It is a literal value, something that is going to be what we call broadcast into the shape of the SOP. And when I do this, this 1 is going to be extended to every entry over here along the rows and every entry along the columns. And then the values over here determined by this equals operator, that if the thing over here is equal to this, then will be 1, otherwise it'll be 0. And because our rows and columns are all equal to 1, everything is going to be 1s like this. We also saw that you can use other comparison operations like less than or equal to. I guess here the 1, 1, everything is less than or equal to itself. If we use strictly less than, then everything is blank. If we change this to indices, indices, less than or equal to, we get that like triangular looking thing. Again, these are the indices along the rows here in the columns. Indices 0, 1, 2, 3, 4. Even though it's displaying hello up here, what's actually being compared is the indices. So that is what the full S operation is. It's the selector of all 1s. And every time we have a selector, we have to get back to an SOP somehow, and that's what the aggregate function does for us. The aggregate takes our selector and takes us back into an SOP. And so aggregates, and then full S comma sequence like this. This is how the function is defined up here, how this is defined right here, aggregate full S sequence. What I've typed in right here is going to give me an error because sequence right here, SEQ, is not defined, undefined variable, because in the function up here, it's defined as the parameter being passed into the average. So I can make this actually work by, say, just assigning something to the sequence like indices, and then do this aggregate. Recall that what the aggregate does is in this selector, for every one of these one values up here, it finds the corresponding location in the sequence and then averages those things together. So the reason why the average function is implemented basically just with aggregate is because that's what aggregate does, is it averages everything together. So we have 0, 1, 2, 3, 4, 0, 1, 2, 3. We map onto a particular row up here. Every one of these rows will have 0, 1, 2, 3, 4 mapped to it because that is the input sequence right here. And then if there's a 1 in the selector, then we will consider the corresponding entry over here and average them together. So because these are all 1s everywhere, every row is going to be all of this averaged together. Any questions as I guess all sort of review from last week, but easy to forget all of this sort of stuff over the break. Any questions about any of that? Okay. The challenge down here, write a running average function. So that is a function will return the average of every element in the sequence seen so far. So here, if we are doing our running average on indices, then the very first entry of indices is 0. So the running average of 0 is 0. The second entry of indices is 1. So the running average of 0 and 1 is 0.5. And then the next entry of indices is 2. So we take 0, 1, and 2 and average them, and we get 1. And then so on. How do we implement something like this? The answer is anytime you are doing something with doing something that you're not looking back into the past, then we change our selector up here. And I have called this, as I've been working, I've called this new selector the mask for aggregation, or mask for auto generation. This is actually a commonly used name outside of the Rasp world for this, but it looks like what we've already seen: indices, comma, less than or equal to, like this. And now when we're on this row here, my intuition behind this sort of shape is that this row, the second position, can't see any of the stuff in the future, can't see the third or the fourth or the fifth position. The second position can only see stuff that's happening right now or stuff in the past at position 1 here. The very last position over here, this can see everything in the future, and the very first position over here can't see anything but itself. But this sort of triangular matrix forces us to have things only look at the past. And this running average can be implemented by, instead of using the full S right here, we use this mask auto generation like that. And that gives us the running average. Actually implementing it as a function, running average sequence, and then return aggregate, aggregate mask ag SEQ, like that. And now I can type in the things that were in the README file, running average of indices, say hello world. This first one here, this first parameter is the actual parameter being passed to the running average function right here. So indices right here is the seek variable right here. And then this function is returning an SOP. I know it's returning an SOP because the output of the aggregate function is an SOP. Aggregate, again, takes a selector as input in the first parameter and another SOP as input in the second parameter, and returns an SOP. And so this whole thing right here is an SOP, and I'm applying that SOP to hello world, averaging all of the indices for hello world. And then I think in the README file, there's some more examples here of it's the same example for all of these three right here, but changing the indices, changing the actual contents of what we are averaging, doing something like that. Yeah,
It
really.
seems like to make that function work, you need to define an SOP previously. Is it like standard to define the SOP inside of the definition of the function?
Let's see, so you're saying that here in this aggregate right here, in order to make it work, I had to define this mask AG right here? Yeah, so, and just to be clear, this is a selector and not an SOP. It's a selector because it is a matrix. And your question is it better to find this inside of the function or outside of the function? And again, this is the sort of language where there are no sort of best practices about things, because Python has best practices because there are literally hundreds of millions of Python programmers in the world. This does not have best practices because there are maybe 1,000 people, and at most they spent like 10 hours working on this stuff, not like a whole career like in Python. So whether you wanted to define this inside the function or outside of the function doesn't matter. And I would recommend doing this outside of the function because this will be something that will be useful in many different functions. But up to you. Does that answer your question?
Yep.
Good question. Any other questions on this or about the homework? Thumbs up.
How many of the homework questions are not possible?
Yeah, that's a good question. I decided to make them all possible for you. So every one of these is possible to implement. Yeah, so I ended up making the homework easier than I originally anticipated. So I guess that question sort of segues us into like the interesting thing about Rasp is talking about like what are the things that are possible and not possible in these transformer models. And so that's what we'll spend the rest of the day here today talking about. It's not going to be something that's explicitly tested in your homework, but it is, again, sort of like the whole point of Rasp. And so this is I think the most important thing to pay attention to today. But before we do that, before we get into that, any last questions about homework or this running average example that we talked about?
How is that like auto?
Like, what does this make? What about this is auto-generative? Yeah, that's a good question. So the reason why I'm calling this, so like the mask AG here, and the AG again standing for auto-generative, is that we're never looking into the past about things. So in some sense, like the auto-generative is thinking about, or one way that people talk about it is that you're just like using it to produce new text, like OpenAI, ChatGPT, auto-generative, because it's generating new text. And here we're not generating new text. But in principle, we could generate new text because all of our like what we're computing here with this L on this row right here, what we're computing is only based on things in the past, and so I could be computing new text here. So like this running average, you could think about each one of these things as being the value that's being output by the model, by ChatGPT as it views each one of these tokens. In this case, it's outputting a number instead of like an actual word or something. But each one of these things that it's computing is only based on like the information in the past and not looking into the future at all. So that's where the auto-generative part comes from. So maybe one way to think about it is that it's maybe not necessarily exactly auto-generative, but it like could be. It has the potential because it's not relying on stuff in the future to make this computation right here. Good question. Okay. So the first interesting thing here about Rasp that we'll see. So again, all the stuff that we've seen so far is from like a researcher's perspective. None of this is interesting. Nothing that we've seen so far is interesting, like how to implement, what are all these weird edge cases about Rasp. None of that is anything that I would consider interesting. The interesting stuff is what Rasp tells us about what a transformer can or cannot do. And so the first interesting thing here is this BOS versus no BOS section. BOS stands for a beginning of sequence token. And it turns out, surprisingly, that if you add just one token, say like a $, to the beginning of your sequence, beginning of your computation, this changes the power of what a transformer can do and makes the transformer more powerful. So one of the simplest tasks that the paper talks about in Rasp is what they call the histogram task. And that means for every input here, like we have this hello, we're going to compute how many times does each one of these tokens appear in the input. So in hello, H appears exactly once, so there's a 1 here. E appears exactly once, so there's a 1 here. But the L's appear twice, so there's a 2 in those locations. And O appears once, so there's a 1 here. So this is the output of the histogram, trying to count how many times each one of these tokens appears. This one here, the no BOS, does not have the beginning of sequence token, no $ up here. The with the BOS down here, hist BOS, does have the $ up here. Same output, except adding a 0 down here. So it turns out you can compute this just fine with or without the $. But it turns out to be a much simpler computation with the $ here.
Why is it printing 0?
Question is, why is it printing 0 here? And the answer is basically we don't really care what the number is here. When we interpret this output, we only care about these last 5 things, making sure that they're the same as this up here. And so it's just an artifact of how the implementation actually is that it does 0. But we could change this to a 1, and it doesn't affect the complexity at all. Yeah, so if we were to use the no BOS version on this string with a $, it would interpret the $, as an actual regular token and put a 1 here. But with the histogram BOS, it's just thinking, oh, this isn't like a real token that I actually care about, so it'll just put a 0 here. My claim is that adding this BOS token simplifies the implementation. And we're not going to go through the details here of these 2 functions, but you can just look at them and see that this histogram no BOS function, so this is the one at the top that did not have the $, this just looks more complicated than this one down here that has the with BOS function. And it turns out that this is in fact a minimal, both of these are minimal implementations. You can't do any better in Rasp than these 2 implementations here. And so adding this beginning of the beginning of sequence token actually made our function much easier to implement down here. The fact that it's easier to implement means that our transformer is more likely during the training to actually be able to learn this simpler function. Simpler functions are easier to learn than more complicated functions. And this is actually something that has people have known about from just experiments for a long time. There were, previous to Rasp, many empirical results that showed that adding this BOS token improves the transformer performance. But Rasp is the first sort of like theoretical contribution that we had about why is this the case. And the reason, again, is because in this particular function, the histogram function. The implementation is much simpler with the BOS token than without the BOS token. Presumably, that's also the case in many other scenarios, but this is the only scenario that there's like this explicit proof of through implementation. Any questions about that? Yeah.
What is the domain problem space of the set of algorithms, or I'm sorry, what is the domain of the set of algorithms, or problem space that a BOS token, for which a BOS token proves? What type of problems?
It's a good question. So there's no known problems where hurts transformer performance. And so this is something that everybody, all models do nowadays, is they add the beginning of sequence token. And there's also something that like, so there's this, when we were using Grok, for example, we were using the chat completions API instead of a raw API. Grok does not expose the raw API. OpenAI has deprecated the raw API. And one of the reasons that all these companies are moving away from the raw API to a chat completions API is so that they are automatically putting in this beginning of sequence token in all of, like, just before the system prompt. And so there's, like, on your end, there's nothing to do for this. This is just something that OpenAI and everybody is now doing in order to make things easier for you all, for us all. But yeah, the actual answer to your question is we know there are some problems that it improves things on. There are no problems that it makes things worse on. So it's used everywhere now. Good question. Other questions so far? Okay, then I want to talk about this sorting section down here next. And this is going to be something that actually will affect like the way that you will see how it has implications for how you do prompting on different tasks. So again, sorting is a standard task. You've implemented it before in like data structures classes. Turns out that many other like reasoning tasks reduce to sorting. So as an example, if I wanted to go from plan a path from here back to my office, I can sort through like the length of all the paths and then choose the one that's the smallest. Or if I want to say like, who is the best president of the United States or that the United States has ever had, then the first thing that I have to do is somehow sort the presidents based on like whatever my condition of best is, and then take the top of those. So sorting, very fundamental. Maybe one more example of that is any coding competition, like leak code thing, will always have a problem. If it's a competition setting, there's always a problem where it just reduces to sorting, and you just have to figure out what's the clever order to sort things in. And you do that, take the top or the 10th element, and then you've solved the problem. So a standard trick in solving leak code problems is coming up with a clever order to sort things in. In Rasp, this is the standard libraries version of the sorting algorithm. And I just want to take a look at that, what the results look like here. So if we have, say, tokens, and let's do sort tokens like this, their implementation requires you to repeat tokens twice. You get this, so ordered alphabetically. And I want to draw this just so we can get a sense about like roughly how complicated this this thing is. Again, so this is a picture of the transformer architecture, which we haven't talked about in much detail at this point yet, but these square boxes up here are transformer heads. They correspond to the select operations, and this down here is the aggregate operation. And so there are 3 select operations in total inside of here, and this one down here depends on these ones up here. So this is still a fairly simple operation here to do this sorting. not much more complicated than, say, the average operation. I don't think we actually drew that. Let's go ahead and draw what running average looks like and compare it. Draw running average. So this only had one attention head. So the sorting is more complicated than taking the running average, but not like significantly more complicated. But some facts here. So sorting cannot be done auto-generatively in Rasp or in any transformer model. And the intuition behind this is because when you have this mask AG, in order to like determine this H right here, what position it's going to be in, you have to be able to look at all of the other things, the E, L, and O, in order to determine where the H is going to go into. But I have implemented for the very first time a auto-generative version of sorting here. And I want us to run it and take a look at it. What this auto-generative version does is if we have an example up here, it looks like this. You will have a one problem that has an input format sort of like this, where your input tokens here are like this is the input, and then there's a $sign, and then what comes after is what you're supposed to output. Let's see. So load this, and I'm going to load this. This file right here is in my AutoGen. Load this, and I want to do this example first. So tokens right now is this BZAY $sign, and these blanks right here, these are the generative part that I want my model to be able to output. I want it to right here output an A because an A is the very first thing in the input sequence over here, and then output a B right here because a B is the second thing. So this is like my prompt over here. This is like the $sign is saying that my prompt is done, and I want my output to be the prompt in sorted order. It turns out that this task by itself is not possible in a transformer where you have the input sequence only exactly once. But if we repeat the input sequence twice, something like this, then so first input sequence and then the second input sequence, then it becomes possible to do sorting inside of a transformer. If you repeat the input sequence twice, it becomes possible to do sorting. And so my sort function is ag sort pass in tokens, and it outputs the tokens in sorted order right here after the repeated prompt. So A and then B and then Y, and then there's not room for the Z, so it doesn't output the Z, but A and B and Y. Why is this not possible in Rasp? So if I do, let's take a look at the mask AG. Here, again, so the B, Z, A, Y, this is my prompt. B, Z, A, Y is my prompt. Just the prompt by itself, not repeated. There's no way for the B to ever see the Z, A, and Y. So there's no way for the B to know what position it's supposed to be in. But if I repeat my prompt and then only consider this part down here, now this second repeated part of the prompt is able to actually view all the other tokens and do the sorting. So repeating the prompt enables sorting, but without repeating the prompt, sorting becomes impossible. This I'm in the middle of writing a paper about this. This is a fact that nobody else in the world knows right now. Again, nobody else has done auto-generative stuff with this Rasp thing, but people have done experiments about duplicating the input prompt. And there's this paper right here that I want to take a look at for a second. Here it is. So it says, rereading improves reasoning in large language models. And so there's a classic chain of thought example right here of Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can now has 3 tennis balls. How many tennis balls does he have now? Well, this, as it's reading this prompt right here up to tennis balls, it doesn't know what the actual question is. How many tennis balls does he have now? And so the transformer is not able to like think about this future thing as it is looking at tennis balls. But if you ask it to read the question again, then when it sees tennis balls, it is able to look back at how many tennis balls does he have now. And so this is going to, in practice, people have discovered that this improves performance. There was no particular problem, though, that people knew that could not be done without duplicating things, but now we know that by duplicating the input prompt like this, we'll be able to actually do sorting, because all of these tokens can now actually attend or view their previous tokens. Yeah, probably very high level, but takeaway here is if you're like whatever you're working on somehow involves something that you might construe as sorting, or you think sorting might be a good intermediate step to whatever it is that you're working on, then repeating your prompt is something that you guaranteed have to be able to do in order for that sorting step to work. Any questions about that? Yeah. Yeah, so that's a good, very natural question about like if we were to repeat things not just once, but twice or 3 times or many, many times, would that affect the accuracy of the results? And they do some experiments actually in this paper. They have if I can find the graph really quick, we'll see that the answer is no. So here is the number of times that it reads the prompt on the x-axis here. And so 1 is the lowest, and then 2, you get the best increase in performance. 3, 4, 5, that performance goes down. And I think this is justifiable in the same sort of reason that, like, if we were to repeat this prompt 3 times, set example BZAY $, BZAY $, BZAY $, like that, mask AG. Then like there's more sort of full blocks down here where everything is able to see everything else. It happens now 3 times, but that's not like any new information available to the transformer. It already was able to do these things. So repeating more than once doesn't actually give the transformer more information than it had before. And so I think that explains why it's not getting better performance. Good question. Let's see. Last time we talked too about like there's these sparse versions of transformers. What a sparse transformer is it modifies how the select function works so if we have this mask long former at size 3, it's like this diagonal along this selector right here. This is what all of these sparse transformers are somehow doing, is they are taking this selection matrix and only using a small part of it. And it turns out that if you're only using a linear part of that selection matrix, so dkn is the total number of elements used by any of these sparse matrices, but sorting we know requires omega n log n comparisons. N log n is bigger than dkn because d and k are constants over here, and is linear, n log n bigger than linear. So sorting will never be able to happen inside of something like longformer or bigbird, any of these sparse transformer models. This tells us, or this gives us some insight into why all of these state-of-the-art models, so things that are released by OpenAI or Anthropic or any of these major companies, Facebook with their Llama models, none of those use longformer or bigbird. None of them use any of these sparse models. They all use dense models. And one reason for that is because if they were using sparse models, they couldn't implement sorting, and sorting is a fundamental task in reasoning. This fact right here is something that the original Rasp paper pointed out, and so something that's at this point fairly well known in the community. An open problem here. This is something that would be within the realm of all of you, one of you, to try to solve it. Is that if you let the number of layers in your transformer or the width of your sparsity, if you let that depend on in somehow, so like setting d equals log in or k equals log in instead of having it be a fixed size, then it's an open question whether sorting can be done using something like merge sort. Nobody knows that right now. Actually coming up with that implementation only really requires some data structures knowledge and playing around with this Rasp program. So this is something that feasibly you guys could contribute to our state of knowledge about transformers. I don't know. This is I feel a little bit conflicted about talking about these sort of things here because everything I said, I would have said in like 60 seconds if I was talking to like my fellow researchers. But I've spent more time than that trying to explain things to you all in a way that you might possibly understand them. But I also realized I went super fast, not going into a lot of details because there are so many details here that we could go into. So a lot of this is probably pretty vague. Does anybody have questions about any of this stuff that we talked about relating to sorting? Yeah.
Has any sort of work been done, I guess, deconstructing existing transform models to see if these sorts of algorithms exist within them, or is this just like theoretical and come from just transform?
Yeah, so the main purpose of Rasp here is to provide a lower bound on we know a transformer could possibly implement this. Actually, in the paper, though, they have like about a dozen or so different algorithms. Sorting here is one of them, and the histogram here is one of them. And they do show that they train some models and show that those models do actually implement they learn from just the data of these particular algorithms here. It's still sort of an open problem though about like trying to dig into the weights of these models and extract meaning out of them. So for like the larger models, like llama models, we don't have any concrete knowledge about like how are they implementing things at this point. I think people would be extremely interested to have some sort of like decompiler that goes from something like llama to a Rasp program, but that's not something that exists right now. Good question. Let's see. One last thing of general implications here. So here's a fact. So transformers can only implement algorithms that have a runtime of O of n squared. So here this n is the length of the sequence. And the only thing that where the length of the sequence comes up in a transformer model or in a Rasp program, is in this attention matrix down here. And so we have n squared operations that we are doing inside of this transformer model. And so if you have we have n squared operations that are happening in this matrix, if you're doing any sort of algorithm that is more than n squared, it can't possibly happen inside a transformer. So some example problems that cannot be solved are any NP hard problem. So these are problems that traditionally have exponential runtime. I very often talk to people where they are thinking that there's been so much progress in AI, transformers, these sort of things that they think their pet problem is going to be solved soon. Their pet problem reduces to one of these problems, like solving a Sudoku puzzle, or all these other ones are a little bit more technical. But it turns out that these all are guaranteed to require more than n-squared computation to solve, and so a transformer will never be able to solve those in principle. There's just not enough compute available inside a transformer to solve those. Another one of these example problems is n-by-n chess. So the details here of exactly what's different between n-by-n chess versus regular chess is not super consequential. You could click this link if you really wanted to know those details. But the idea is that you need n different tokens, in different letters to encode the positions on the chessboard as the chessboard size grows. And this is actually harder than NP-hard. It's exponential time, exp time complete. And so a transformer will never be able to solve this sort of generalized chess game. They can get like decent at chess. ChatGPT is better than me at chess right now, but it's never going to be able to solve chess the way something like AlphaZero solved chess. It's a totally separate technique. Transformers can't do it. Another problem, a lot of math problems have different runtime bounds. The simplest one that will never be able to happen inside a transformer is matrix multiplication. We know that that takes time at least n squared log n, which is bigger than n squared. And so a transformer will never be able to implement matrix multiplication. And again, a lot of logic problems sort of reduce to encoding things by a matrix and doing a multiplication. And so there are a lot of logic problems that a transformer will never be able to solve because it can't solve matrix multiplication. Another fact right here, so it's not every algorithm with a quadratic complexity will be implemented by a transformer because we only have n-squared comparison operations like the equals or the less than or equal signs. If you need n-squared like additions, that can't be done with a transformer. You only have a linear number of additions. And again, these sparse transformers, not used in practice in any of the major companies because you can only do linear runtime algorithms instead of quadratic runtime algorithms. So that's a major handicap for those algorithms. Yeah, so one of the reasons why I liked Rasp, wanted us to talk about Rasp first with transformers is these are all, I think, sort of like, in some sense, very trivial results of Rasp that once you realize that this matrix right here is the only place that like computation can happen, where it depends on the size of n, then all of these results about like what can transformers do in principle follow immediately from that. And I rely on this very often when I'm thinking about like, can a particular problem ever be solved by a transformer or not? Any questions about any of that? Yeah, I realize that's still a lot of high-level things. Probably I mentioned a lot of problems here that people aren't super familiar with. But if in the future you're ever thinking about like, is there some particular problem that will a transformer ever be able to solve this or not? This is the first easy tool to think about. Like, it doesn't matter. This is all independent of training. Doesn't matter like what cool training stuff is developed in the future. Transformer can never do any of these things, even if it's like the best training method possible. Because this is just fundamental to the architecture, that the architecture can't do any of this stuff. Maybe if you do think of, if anybody has any problems that they're interested in about knowing whether a transformer can solve them or not, you can bring those to me and we can work through some of this reasoning to see like, is this in the realm of feasibility or is this outside the realm of feasibility? Any questions? Yeah.
So you more specific, you're talking about having a Sudoku solver, for example, that answers a certain problem and dimension be solvable. Like, could you have one that's like pretty good at solving?
Um,
What's the threshold?
yeah, so the good question. So for all of these NP hard problems, we know that there exist like the vast majority of solutions. If you were just to pluck a solution or pluck a problem out at random, the vast majority of those would require exponential time to solve these. So if you were to randomly generate an n by n Sudoku, it would require exponential time to solve. That doesn't mean that all Sudoku problems require n by n require exponential time to solve. There are some that are going to be easier to solve, and like if you get a beginner's Sudoku book, they will give you some of those easier ones to solve. So possibly like you could have a transformer model that could solve some of those easier ones, or that could be like provide hints to people about like what are the next good directions to explore in Sudoku. But the vast majority of Sudokus just selected out at random, not going to be solvable, require exponential runtime. This theory of like NP completeness and finding sort of like good enough solutions to NP complete problems, or solutions that are, or thinking about whether a problem is like almost hard or like really, really hard. This is all stuff that would be started to be covered in the graph algorithms course that Professor Cannon teaches, but it's really like a graduate level algorithms course that starts talking about this stuff in major detail. Yeah, good question. The proper full answer to that would be like a full year's worth of course.
Just to clarify, this is just for like one turn generation. It might be solvable, let's say, if you're step by step or some other model.
So the one sort of like workaround to this sort of general implications, all these things, is you could potentially ask a transformer model to like write Python code that would then solve the program. There's a few more gotchas with that, but that allows more computation to happen, because then the Python program would have however much computation that the Python program has.
But what about like for something like one
As long as it still has this like attention matrix right here, then it's limited by that n squared compute. So one of the things that's happening in something like O1 is that it's expanding this, like maybe it only shows you 100 tokens when it used 1,000 tokens. So for there, the n that's available to it is 1,000 instead of 100. And so if they were to make their n somehow like larger than linear on the size of your query, then they could go to like a cubic runtime up here. Did that sort of make sense?
Yeah. So that, but that would potentially be solvable through like roundabout.
Yes. So Sudoku still would not be solvable because that's going to be exponential. So you need an exponential number of tokens, and that's not going to be like feasible in practice. Yeah.
Are there other architectures people have come up with that can handle higher runtimes?
Yeah, so other architectures that people have come up with. So the standard like recurrent neural network doesn't have this limitation. It can implement essentially any algorithm. It's just much harder to train in practice. So people were very skeptical at first about like the transformers coming out because of various limitations like this, and but we sort of stuck with them because they're just easier to train and practice than the more complicated models. Let's see. The other thing that I wanted to do today was start going into a little bit more detail about the transformer model and how it relates to into the Rasp programs. And so I'm going to draw some pictures about the transformer architecture and start seeing how those relate to the Rasp programs here. So again, this is not something that's at all graded, but might help give you some motivation for why this like Rasp stuff is a interesting tool. So the picture that I'm going to draw over here on the left-hand side, I'll start writing some tokens, HELLO. And so I'll just use the same example that Rasp used here of each individual letter being a token. Again, the tokenization step, not super interesting from a model power perspective or how what the transformer architecture is capable of doing. That however you tokenize, it doesn't affect anything downstream. But each one of these tokens, so these are the tokens right here, they're going to get mapped into some higher dimensional space. And this mapping happens, it's just like a one-to-one mapping where we store a vector for each of these tokens. And the size of each of these vectors is going to be D. And so if the total number of tokens that we have here is L, so L is the total number of tokens, then this right here is a L by D matrix. And this matrix here is like the actual input into the transformer.
What is D?
D here is, I'm using the letter D for dimension. It's the dimension of these input embeddings right here. In modern models, D is typically going to be somewhere between like, somewhere around 10,000-ish. Again, like ChatGPT, Claude, Anthropic, they don't publish these sorts of details. I want to say for, I was just reading this the other day about Llama, it was, I think, 16,000, something along that line. But it's a very big number here about the dimension. And my intuition about like these tokens is this tokenization process, these dimensions, is that this is where like all the actual facts of the model are stored. Like the facts are stored here in this tokenization. So if there's one of the actual tokens in all of these models is Trump, another one of the actual tokens in all of these models is Harris, and one of these like feature dimensions inside of here is going to be how political are those words, and those words will be a very high political like valence inside of here, whereas other words like yellow will not be very political. Then, but this is something standard every language model ever has always done, convert your token somehow into a vector. What's new about the transformers is there's these three matrices, the K, Q, and V matrices. And I want to explain how these three matrices relate to this Rasp model. Each one of these matrices is going to have shape D by D. All three of these have shape D by D. And all three of these matrices are individually multiplied by each one of these input tokens right here. So H, have our input value what it is, and this K value, whatever is inside of here, do that multiplication. And similarly, Q, and V, all multiplying on these dimensions right here. In the attention matrix, we have been drawing these only as strictly as matrices, but really there's like a, so they have a more like three-dimensional tensor shape, where this final shape out here is also in like d-ish dimension. And when we do this k multiplication on this first token, that gives us the position 1 right here. The k multiplying on the second token, whatever this token is right here, that gets multiplied by k, and then the result gets stored in the second position up here, and so on. So the stuff that's up here is all the k times the input tokens. And similarly, the stuff that's stored right here, this is all the Q matrix times the input tokens. This is all Q times the input tokens. One of the things that Rasp assumes is that the values of our K and the Q are all going to be binary. It's doing like a binarization step. So the reason we get just like trues and false in our comparisons down here is because of the binarization of this K and the Q. But that's not, it doesn't really affect the power of the transformer. Or it doesn't increase the power of the transformer. It can only decrease the power of transformer. So Rasp binarizes K and Q. That can't increase, does not increase the power. And so the matrix up here that we're creating with the select operation is a combination of the K and the Q, and all the code that you're actually writing in Rasp is the contents of K and the Q. So instead of learning the contents of K and the Q here, you're writing the code that's the contents of the K and the Q. And then this V over here, this is the, when we do the aggregate here, the selector is the first parameter, and then this V stuff is the second parameter. So the second thing that we put over here that is an SOP is this V parameter. Every one of our SOPs is one of these input dimension things times one of these K, Q, or V matrices. And so we have a bunch of SOPs up here, SOPs over here, SOP down here. And it's always, yeah, our input SOP somehow times a K or a Q or a V. The last step in the Rasp model that we're allowed to do besides the aggregate and the select operations is we're allowed to do the arbitrary computations on that are component-wise. Arbitrary component-wise ops. And so again, these are not part of the attention head. Everything I drew up here with the K, Q, and V, this is the attention head over here. The arbitrary component-wise operations, those are the, there's a feed-forward neural network. Feed-forward neural network that sits between each one of these attention heads. And it's known that feed-forward neural networks, they have arbitrary compute computation. Any function can be represented as a feed-forward neural network. Can represent any possible function. And so the reason why we're allowed to use arbitrary component-wise operations in Rasp is because feed-forward neural networks can do arbitrary computation. And the interesting parts are, again, how this K, Q, and V integrate to each other, how the select matrix up here and the aggregate down here integrate. A few real quick facts are that it's known that if you are allowed to use, say, rational numbers instead of somehow discrete numbers on any language model, whether it's a transformer or RNN or anything else, it's known that P equals NP in that situation, and you can solve exponential time problems in just polynomial time. And it's also known that if you're allowed to use the irrational numbers instead of just the rationals, then you can solve non-computable problems like the halting problem. But as soon as you do any sort of restriction beyond the rationals to some sort of finite representation of the rationals, then that's equivalent to just doing binary for everything. And so nobody thinks you're really losing any power in this Rasp binarization step right here. Another thing that is interesting to note here is that the indices values hasn't come into this in any way at all. And also the length of the transformer hasn't come into this in any way at all. And so the actual transformer model itself with this K, this Q, and this V parameters, these don't depend on the length of the input. They don't depend on your context window size. And so even models that say they have, say, like an 8,000 token context window size, it is possible to use them for an arbitrary context window size of, say, 100 million. They just haven't been trained in that situation, and so we don't expect good performance on them. But it is possible to use them. Let's see. That's pretty much all the time that we have for today. We might talk about more stuff like this next time. I'm not sure exactly yet what we'll talk about next week. But definitely no more like Rasp specific stuff. If people have questions about any of this or about project stuff, happy to stick around and talk about that. Otherwise, good luck on your homework, and please get your project proposals into me.